I'm going to jump ahead in the book a little this week, interrupting our discussion of kinematics, which describes the motion of things, and talk about Newton's laws, which tell us why motion occurs in the first place and how it is affected. The point of this is to understand motion from a causal perspective. And it turns out that forces are what affect motion. Conceptually, a force is a push or a pull acting on an object. It's a vector. You can have more than one force acting on an object at a time. Since it's a vector, we can describe it by a magnitude and a direction. The magnitude of the force is simply how hard are you pushing, how hard are you pulling. Sometimes the word strength is synonymous with the magnitude of a force. And direction, of course, is which way are you pushing or pulling on the object. Which way is this going to tend to make the object go? Net force is just the sum of all forces acting on the object. Since forces can add together as vectors, they can oppose each other if they have different directions. Is the vector sum of all forces that act on something. This can turn out to be zero in the case when there are no forces acting on an object. In principle, that's possible. In practice, it never happens. A net force can also be zero if all the forces acting on the object exactly add to zero. That can happen. And Newton's first law tells us what happens in the case of forces adding to zero, and it qualitatively tells us what happens in the cases when forces do not add to zero. The reason Newton's first law is important is that it tells us something about the natural tendency of motion, and it gives us a first glimpse into what controls the motion of things. So we'll start with classical view of physics before physics was actually brought into the modern age by Isaac Newton, from Aristotle, who was a really smart guy and kind of gets a bad rap for his physics because it turns out to be wrong, but it made sense and it seemed consistent with what people knew at the time. So it's really kind of unfair to criticize it. However, it's also improper to cling to his physics instead of using the understanding that we have now. In Aristotle's view, different kinds of things had their place. So the light elements, air and fire, would tend to go up. The heavier, baser elements, earth and water, would tend to go down. Once they reached their places, they would stop. That would be their natural tendency, would be to rest in their correct places. The heavens were something different. They were a fifth element. They moved in perfect circles, with some exceptions which garnered a lot of attention. Those exceptions included the planets. Their perfect circles did not go with the rest of the heavens, and they had some changes to their circles, which were modeled by trying to add circles to circles, which eventually didn't work once measurements of those motions became more and more accurate. And also comets were a real problem because they were not even regular. And so that's why comets were often portended as dire warnings of horrible events coming, because what they were themselves such strange objects. Different kinds of motion, other than going to the natural place, required some kind of intervention, some kind of force. And those different kinds of motion were referred to as violent motions. So of course comets were a result of violent motions, but so was anything that happened on Earth, such as throwing a ball, moving, pulling a wagon, riding a horse. All of those things required violent motion, intervention by an agent. This view was challenged in the modern age, beginning by Galileo, and then it was codified rigorously by Newton. I like this picture of Newton. It's not actually what Newton looked like, but it's a representation of Newton by William Blake, who actually didn't like Newton, what he did. But what we have here is this man who is formed from formless rock. You see he's kind of coming out of the rock, bringing order to the universe. Here's one way of stating Newton's first law, that an object's state of motion does not change unless a non-zero net force acts upon it. So, if there is no net force acting on the object, or if the net force acting on the object is zero, then if it's at rest, it remains at rest. If it's in motion, it continues moving in a straight line at a constant speed. Well, what does this mean? If it's at rest, it remains at rest. That means its velocity is 0. If it's moving, it continues at a straight line at a constant speed. Well, that means constant direction, constant speed, therefore constant velocity. Zero velocity is also a constant velocity. So what Newton's first law is telling us is that if the net force acting on an object is 0, that object has a constant velocity. We can state this formulaically as the sum of all forces. That's what that sigma means. That means a summation, adding together. So the sum of all forces acting on an object is 0, is equivalent, that's what that double-sided arrow means, is equivalent to acceleration being 0. If acceleration is 0, then velocity is constant. A 0 net force means constant velocity. This is a very strong statement. Notice the double-sided arrow. It also means that if there's constant velocity, or 0 acceleration, then we know that the net force acting on that object is 0. This is against what Aristotle said. And it's against common experience. It's against what you might expect. It's against intuition. Can we modify our intuition to understand that this is actually the case, to understand what we see in our regular experience as being consistent with Newton's first law? Newton's first law is not just a theoretical construct. It's something that actually happens all the time, that's always valid in all situations. So think about it. If you are moving in a truly constant velocity, say you're cruising in a plane that's not meeting any turbulence, so it's not bouncing up and down, but it's moving at a constant speed in a straight line, or in a car on a level straight stretch of roadway, or on a train on a smooth track, do you feel any force that's moving you forward? Or do your surroundings seem to be still even though you know they're moving with respect to the earth around you? The answer is, of course, you don't. It feels perfectly normal. You feel like you are in the frame of reference at rest, even though you know you're moving along. And that's what Newton's first law is telling us, essentially, that constant velocity, any constant velocity acts, as far as the laws of physics are concerned, like any other constant velocity. It turns out that this is an important concept even when we get to modern physics with relativity, the idea of an inertial reference frame, the reference frame that's moving at constant velocity. Galileo made an interesting thought experiment to get this idea across. If you were in a closed box, a closed container, moving at a constant velocity, is there any experiment that you could carry out to tell if you were moving or if you were still? Galileo concluded that you could not. Einstein also concluded that you could not. And that's our current idea in physics, is that there is no difference, theoretically or in principle, between a constant velocity and any other constant velocity. So, being at rest is not some special thing. Like in Aristotle, being at rest was the natural state of objects, at least earthly objects. The natural state is constant velocity. So here I'm showing as a Venn diagram the state of constant velocities, and being at rest is just one of them.